Suppose you're in a game show and you're given the choice of 3 doors. Behind one door is a prize car, and behind the others, goats. You pick a door, say number 1, and the host, who knows what's behind all the other doors, opens another one, say number 3, which has a goat behind it. He says to you, do you want to pick door number 2? Then, is it to your advantage to switch your choice of doors? This is the famous Monty Hall problem, as posed to Marilyn vs. Savant in the Ask Marilyn column in Parade magazine in 1990. It's important to note that the host, loosely based on the game show host Monty Hall, knows everything that is behind these doors, and will always choose to reveal one of the 2 doors that you haven't chosen yet, and will never choose the door that hides the prize car, and, under standard assumptions, must always offer the chance to switch between the original chosen door and the remaining closed door. The first impression for an astounding majority of the public is to say that each of the 2 remaining closed doors have an equal probability of revealing the car, conclude that switching doesn't really matter. This seemingly makes a lot of intuitive sense. After the host has opened a door, you know that there are 2 closed doors and that one hides your prize and the other a goat. But as Marilyn discussed in the column, this is incorrect. This is an example of a veridical paradox, as the solution is so counterintuitive it seems absurd, yet is demonstrably true. The answer? Yes, you should switch. The first door has a 1/3 chance of winning, whereas the second has a 2/3 chance. Savant discusses multiple reasons as to why, in an attempt to quell the counterintuitiveness of it. First is to suppose there are a million doors, and you pick door number 1, and the host, who always avoids the one with the prize, opens all except door number 777,777. It seems pretty intuitive then to switch to that door pretty quickly, doesn't it? Next, let's look at a table of all equally possible outcomes, that is, positions for the car, where you start with choosing door number 1. Here it is clear that in 2 of the 3 positions, switching will win you the car. Now, perhaps more mathematically, let's look at the 3 doors before choosing any of them. We know that the singular car is in one of them, so the probability that each of the doors has a car behind it is equally 1/3. We can therefore choose any of the doors and know that there is a 1 in 3 chance that a car is behind it. I'll choose the first door for simplicity's sake. It's reasonable then, since probabilities must sum up to 1, to say that the probability that the car is behind either one of the 2 other doors is 2/3. Now is where most slip up in the reasoning. When the host opens up one of the non-car doors, one can imagine that alters our information about the scenario, letting us change the probabilities to half and half. However, since we knew all along that this was going to happen to some random door, they remain 1/3 and 2/3. It's just that instead of the 2/3 probability being split over 2 doors, it describes a singular door, the one you wish to switch to. Well, actually, we are given some information, but only where that 2/3 probability is going. Nothing changes the fact that your initial door has a chance of 1/3 of hiding a car. In other words, it's the fact that the host chose to open a specific door that provides the greater probability. The most interesting thing about this problem is not its counterintuitive behavior, but rather the public's backlash to it. After Savant initially answered this in her column, multiple people, even professional mathematicians, retorted and called to say that her answer was an error. As she continued to defend her deduction, even more began to criticize her. All in all, she said that about 92% of the general public and 65% of the responding universities, a total of 10,000, insisted upon her being wrong. So she invited schools around the country to set up an appropriate experiment, following the same rules as outlined in the beginning, and sure enough, now nearly 100% of the responding public seemed to believe that it paid to switch. Funnily enough, she included the replies of some who still didn't in her last letter on the problem. Probability is the study of mathematics that seems to extend logic and deals with limited information and how a change in information affects the outcome. We were dealing with a magic fairy tale of a mathematical puzzle, one where the host would act always predictably, randomly, fairly. But that doesn't sound much like the real world, does it? Anyhow, thanks for watching and tune in for next time.